Hello everyone, my name is Daniel Michek, and I'm a senior manager at Altera. I'm responsible for Altera's AI software strategy and deployment. Throughout my career, I've been at the forefront of launching transformative products that redefine performance metrics and optimize deployment costs. But I think our real focus should be on the practical applications of AI, where size, weight, and power are paramount, ensuring solutions are both efficient and scalable. Today's session will examine some of the total cost of ownership aspects of implementing AI inferencing at the edge. To illustrate some of the technical and business decisions, we'll show multiple actual customer examples, including two where customers are using transformers and feature extraction. Training is dominated by large CPU and GPU clusters in data centers and the cloud. For various technical and business reasons, inferencing in the cloud is now moving towards the edge. Let's quickly examine three operational models for implementing AI. Streaming involves raw data collection and aggregation at the edge, with all of it sent back to the cloud data center for training and inferencing. This is expensive from a capital expense point of view because extra silicon and memory need to be added to the servers. Operating expenses can also be higher due to high power consumption and network bandwidth used. Option 2, edge preprocessing and feature extraction, helps to alleviate some of that bandwidth because you don't need to send as much data over the network to the cloud. But latency is increased dramatically because of the networking delays with packets going back and forth between the edge and cloud and data center. Too large of latency doesn't meet the requirements for edge-based decision making. Option 3, inference at the edge, is now a focus area for the AI industry. Keep in mind that edge inferencing requires very low latency because decisions need to be made in real time. To keep operating expenses as low as possible, edge AI inference needs to be implemented in a way that achieves the performance and latency needed while optimizing for low power. Looking at these three options, we begin to realize that the AI solution for edge inferencing is different and diverges from high-end cloud-based training and inference. In fact, this realization is already resulting in changes across the AI landscape. Can you guess which company this quote comes from? You guessed it. The quote is from NVIDIA. If the market leader in GPUs thinks AI inference should be moving to the edge for real-time decision-making, we should look more closely at this trend. Let's review a common use case for many industrial customers who wish to utilize AI inferencing to continue increasing their factory's efficiency and throughput. The industrial customer has an existing manufacturing plant and is willing to invest to add AI capability if it results in a large enough increase in throughput or efficiency. Let's look at three options for adding AI. The first option might be to add AI, but implement it via a store and analyze later methodology. This non-real-time option could be relatively easy to implement and not too disruptive to existing processes or procedures. However, there is the risk of falling behind the efficiency curve since updates are only implemented infrequently. Option 2 is to add real-time AI inferencing by adding GPUs to the factory data center. However, in this scenario, it requires more data transfers between the factory floor sensors and the factory data center, and the latency needs to be low enough to allow real-time decision-making on the factory floor. We have customer evidence that GPUs targeted for edge inferencing may not have the desired performance or performance per watt desired by customers. Also, the legacy Ethernet wiring might be a bottleneck for the anticipated amounts of real-time network traffic. In this scenario, the customer has the option to rewire their plant to 10 gigabit Ethernet, but this is costly and requires even further capital expenditures. Finally, we look at the third option, which is to move the inferencing closer to the sensors where we can combine the image processing algorithms with AI inferencing functions. This does require some investment, but not as much as other options, and there are several key advantages to using an FPGA in this scenario. The price to add the FPGA for AI inferencing may come at zero cost, since FPGAs are already used in many factory applications. A large percentage of industrial programmable logic controllers, or PLCs, and other industrial equipment have been using FPGAs for decades for workloads ranging from sensor fusion to image processing and motor control for industrial robots. So in this scenario, option 3, the FPGA can continue to be used for image processing and directly feed that into the AI inferencing algorithms to find and detect potential defects and make a real-time decision on how to handle those anomalies. There can also be periodic updates back to the factory data center over the existing gigabit Ethernet legacy network so that any updates to the AI, either the model or the weights, can be calculated and analyzed for potential updates back into the FPGA inferencing engines. Because the FPGA has hardware flexibility and can be reprogrammed while still installed within the field, any future AI enhancements can easily be implemented. In the previous several pages, we mentioned two different types of semiconductors used for AI. So let's switch gears for a little while and look at the relative performance of different AI inferencing workloads from a semiconductor implementation viewpoint. We've plotted the estimated performance relative to each other, and that's why there's no scale on the y-axis. Across the x-axis, there are 4 commonly used AI models. Our first implementation uses custom-designed ASICs to implement each AI workload. You see 4 columns here to represent the 4 different ASICs needed, because each ASIC is tuned and optimized for a particular solution. Different solutions generally require a different amount of processing or memory, as many AI solutions tend to be compute-bound or a memory-bound problem. The second implementation uses GPUs, and the GPU you use has better broad solution capability, but it still gets optimizations for specific AI solutions. And the third type of devices used are FPGAs. FPGAs have the ability to be modified in your design cycle so that you can tailor your resources to match the compute and memory needs for your specific AI solution. Let's discuss the graphed results by examining the technical and business implications for each semiconductor type. ASICs are great for implementing one specific AI function, but have a few key drawbacks. First, a large NRE is needed, and relative performance drops off dramatically for other kinds of AI models. Also, you can't iterate quickly or cheaply to handle new AI variants that may arise in the future. Furthermore, what is the life expectancy of this customized product that the ASIC supplier is manufacturing for only one customer? GPUs were quick to develop and target their technology for AI. They're good for general-purpose DSP, AI training, and CNNs, but performance drops off for classical machine learning RNNs and LLMs. FPGAs are also general purpose, just like GPUs, and have long been used for many DSP-centric workloads, such as radar processing. However, FPGAs aren't typically known for being used for AI applications. That has been slowly changing over the past 15 years, and recently we've seen a large increase in FPGAs being used for a variety of AI inferencing workloads. Because FPGAs have flexible hardware, you can tune each AI model and workload for the highest performance, lower power, or optimal combination of performance per watt from the ground up. The flexibility of FPGAs also allows you to quickly iterate for new model variants and retrofit field-deployed equipment. Another key benefit of FPGAs is they tend to have much longer life expectancies, typically 10 to 15 years, and many times even longer, which are better aligned with edge application lifecycle requirements. Each of these 3 semiconductor options has its pros and cons. For those technical people watching this session, you probably aren't convinced FPGAs can achieve the performance shown here. Let's move on to review a head-to-head comparison between FPGAs and edge-focused GPUs. Here we've plotted the results for one specific benchmark using the ResNet 50 model, which is commonly used when comparing different AI products. You can see Altera's Agilex 5 FPGA has a sizable advantage in frames per second when compared to an AI-focused competitor's FPGA. Even more interesting, the Altera device is also significantly faster than the GPU recommended for edge AI applications. When you factor in the device's power consumption, the Altera FPGA advantage over the GPU is even greater than just the raw performance. FPGAi is the tight coupling of programmable logic with artificial intelligence. If we organize the recent FPGAi usage into application groups, we see the emergence of 3 main types of AI workloads used by Altera customers. The first 2 groups show the FPGA used for a wide variety of edge, generative AI, or custom AI workloads. In these two groups, inferencing can be accomplished in the FPGA based upon pre-trained models that you've developed. More recently, customers have discovered the value of using an FPGA next to a high-performance GPU. Since we have a limited amount of time in this virtual session, we will not discuss those details here, but suffice it to say, FPGAs are ideal at pre- and post-processing of the data being fed to the GPUs, as well as managing the data transfers for the servers and the GPU board management too. Let's move ahead and examine specific customer examples, what they have publicly said about their Altera FPGA usage for AI workloads, along with some technical details for implementations using transformers and feature extraction. Shown here are a trio of recent public statements from our customers who have implemented AI inferencing using FPGAs for edge workloads. Stryker is using the FPGA to examine and locate areas of interest that doctors can examine more closely, such as locating a tumor for medical imaging applications such as MRIs, CAT scans, or X-rays. XOR is using the FPGA for its newest generation of industrial programmable logic controllers, commonly referred to as PLCs. Tiami is a wireless vendor that has found a novel way to utilize the 5G spectrum for ambient RF sensing, resulting in personal detection and location services. But FPGAs are good at AI solution implementations that go beyond CNNs too. This customer testimonial comes from startup company Positron, which is using Agilex 7 FPGAs for a large language model implementation. In their implementation, two key business metrics are dramatically better compared to GPU-based implementations, and Positron has a roadmap to further tune its FPGA implementation to get even better results in the future. This next customer is Myrtle.ai, whose solution is already available in the market today. The customer quote is from Liz Corrigan, Chief Product Officer at Myrtle, and we're highlighting this specific customer workload because Myrtle has concluded that using a vision transform model achieves better results than a CNN model for image classification, segmentation, and object detection, especially in noisy environments. Please note that they've chosen the FPGA because it has the lowest latency of any other platform in the marketplace. The graph plots the results of the vision transform versus the CNN results, including the effect of pixel corruption on the satellite imagery used for this benchmark. Accuracy on the y-axis versus increasing percentage of information loss on the x-axis. The transform model results are the red-colored line. In this graph, being higher compared to the CNN results in better. Myrtle claims the FPGAs provide additional benefits to them: accuracy, scalability, flexibility, and the ability for compression and decompression. Let's now look at another customer using FPGAs for AI in a high-performance computing application. Our next customer is the European Southern Observatory, and one of their programs is the Chernikov Telescope Array. They have published a paper documenting their research into picking the best semiconductor device for their unique hardware design, which will be used within an interconnected array of telescopes. Their conclusion was to use FPGAs for the camera data acquisition model, as their research results showed several key advantages over the leading GPU and other FPGA vendor products. Before discussing the customer's technical details, some might not understand what we mean by the term feature extraction, so let me define it this way. Feature extraction is the process of simplifying data by selecting and transforming relevant information for model training. It reduces dimensionality, resulting in improved model accuracy and faster computation. So why did the CTA use feature extraction with the FPGA? They wanted to improve event reconstruction, achieve better noise reduction, and do it all in real time. Using the FPGA-based design, the CTA team can extract the following key features: Cherenkov radiation patterns, energy and direction of incoming gamma rays, time of flight of particles, and spatial properties of the radiation shower. The FPGA results are technically impressive while also coming in at a lower overall total cost of ownership. Furthermore, the engineers at CTA think they have more room for improvement, as they have yet to fully explore and utilize all of the available FPGA features. As we begin to wrap up this session, we've shared data and customer evidence showing that FPGAs are viable products for various AI inferencing applications, especially edge workloads. FPGAs uniquely offer application flexibility, and Altera devices have specific silicon features useful for AI algorithms. The Agilex portfolio of FPGAs delivers the capabilities needed to thrive in the new era of FPGAi. In addition to hardware acceleration, Altera FPGAs alleviate bottlenecks for memory-bound AI workloads like LLMs. For compute-bound AI problems, such as CNNs, the Agilex 5 and Agilex 3 families provide the only FPGA fabrics infused with AI. These families enhance our traditional DSP blocks with AI tensor capability, which are embedded into the core fabric to vastly increase the amount of AI compute. And FPGAs generally have long life support, lowering the risk of obsolescence compared to GPUs, microcontrollers, chipsets, or ASICs. For Altera's newest products, we estimate life cycles of 10 to 15 years or longer. In fact, some of our existing Max and Cyclone product families have an estimated end of life in 2040, which means their planned lifespan is between 15 to 30 years. Altera has also created software to make it easy for existing FPGA developers and non-FPGA AI experts to create optimized AI inferencing solutions. FPGAi is not just about hardware. Altera's FPGA AI suite is the cornerstone of our FPGAi strategy, offering a seamless design automation environment for embedding AI inference engines into Altera FPGAs. It bridges the gaps between AI model development and real-world AI deployment by ensuring compatibility with leading frameworks such as TensorFlow and PyTorch through the OpenVINO toolkit, which is an integral part of the environment. Because FPGAs already have a large presence in edge equipment performing functions such as sensor fusion, image processing, and multi-axis motor control, we believe the CapEx to add AI workloads in FPGAs is minimal when compared to ASICs or GPUs. We showed customer examples of how FPGAs have the flexibility to add various types of AI functions, including transformers and feature extraction, for a variety of edge workloads. FPGA adaptability allows for quick design iterations, so customers are assured their products are future-proofed for implementing any new models or algorithms that might be invented in the future. Here is why you should consider Altera's FPGAs for edge AI. Altera's leadership in AI inference performance per watt enables customers to reduce power consumption and electricity usage, resulting in lower OpEx compared to edge-focused GPUs and other FPGA vendor products. Altera has the best FPGA product portfolio with innovations to address AI requirements from cloud to edge applications, so customers only need one FPGA vendor to focus on. And Altera's AI software is getting great reviews and feedback for its usefulness and ease of use. Use the QR codes below to learn more, try our AI software, or have a salesperson contact you. Thank you for your time and attention.